How y'all doing? I think I asked that already. Let's see. Happy Friday. And main goals for today are on Wednesday we started looking at different collision types. We started a elastic collision between two vehicles. Today we're going to finish that out and talk a little bit about what we're going to be doing next week. Before we get started, any questions, needs, concerns, etc. from anyone? Anything on your minds? All right, let's get started. My computer does this thing sometimes where it just blanks out and I have to close it. So now we'll get started. So, to briefly review, we began looking at different types of collisions and the effect that that has on both momentum and kinetic energy within those collisions. Momentum is conserved in all types of collisions, but what happens to kinetic energy depends. Inelastic collisions, the boring and fairly common type, usually happens when two objects that are not elastic collide. The objects tend to stick together. They don't bounce away from each other usually, and they're very boring, they're very low energy since the kinetic energy is not conserved from start to finish in an inelastic collision. Whereas in an elastic collision, kinetic energy is conserved because elastic objects are able to store the energy for a moment before releasing it again, rather than just crashing and losing it. So elastic collisions keep their kinetic energy, and for that reason, the collisions are more energetic. The objects tend to ricochet off from each other and fly away at pretty high speed. Like the speeds are bigger than just inelastic collisions where only momentum is conserved. The momentum is still conserved, it's just the KE is conserved alongside it. And because of the differences between the two, vehicles are designed so that if they crash inelastically, because you don't usually want vehicles to ricochet off from each other and fly away at high speed. And the question we began doing is we looked at we're trying to investigate what a hypothetical car crash would look like if it were elastic and prove why that would be a bad thing. So the two cars that we are colliding, I've got two different self-driving cars from fiction so that there's no humans involved. Sports car and truck driving at each other at the same speed. Note very big mass differences between the two. We looked at the conservation of momentum here, concluded how much momentum is in the system initially. There's a lot of it, and note that it points in the leftward negative direction. It's because momentum is a vector. And if the system's momentum points to the left, that is a very bad thing for the sports car that wants to go to the right. Now on the final side, the issue we ran into is that in elastic collisions, it's often very likely that the objects are going to ricochet away from each other at different speeds in different directions. And therefore we cannot guarantee that the two final speeds are the same like they would be in the arrow that we launched at that wooden log at the start of the chapter. In that case, they stuck together, they would have the same final velocity. But here we cannot guarantee that. In fact, it's quite likely if this is an elastic collision that the objects would not have the same final speed. So we have to treat them as separate variables, and that means that this equation has two unknowns in it, meaning that it is unsolvable by itself, and we need a second equation with the same two unknowns. Now, conveniently, elastic collisions have lots of equations that we can use to describe the motion of the objects involved in them. For example, if kinetic energy is conserved like momentum is in an elastic collision, then we can treat the conservation of of kinetic energy in much the same way. Compare the initial total kinetic energies to the final totals, and we could land at a very similar looking equation since kinetic energy and momentum both rely on the same variables, mass and velocity. So conservation of kinetic energy can also give you a formula with the same two unknowns in it, VF car and VF truck. And so this could be a second equation with the same two unknowns in it. We can combine the equations as we tend to do in that scenario. The only problem with the kinetic energy conservation is just that the kinetic energy formula inherently has a squared in it. And that means that if we try to take this and solve for VF car, the equation has a squared inside of a square root. And this can get kind of ugly and kind of complicated to work out. We would have to take this, plug it in over there, work out the square root, then resolve the squared as well. It's just kind of a pain. It works, it's just not very fun. And for that reason, rather than using this formula directly, I recommend using this formula that was derived from it. This equation is designed to compare the initial and final velocities of two objects having a one-dimensional elastic collision. So it's kind of doing the same thing as the conservation of kinetic energy. It's just some very smart people took all of this and simplified it down into just V1 initial minus V2 initial equals V2 final minus V1 final. Note that the order does change between the two sides. That is on purpose. That is not a typo. You have to pick which object is 1, pick which object is 2, and then put them in the correct places here, or else the formula doesn't work. It's a very useful formula. It just has the caveats on it that it only works for a one-dimensional elastic two-object collision. One-dimensional meaning things are only moving forward or backwards. It has to be elastic. This formula does not work for an inelastic collision. Inelastic collisions, comparing momentum is your only option. Elastic collisions, you have more options, and this one is kind of the one I like the least. I like this method. Fewer variables, no squared in it, and how we can use that here is, we know both vehicles' initial velocities, and so we can set it up as a second equation with the same two unknown final velocities. Use this as our second equation with the two unknowns, plug it into the other, and it'll be easier than using this one. This one will work, I just don't like it. I like this one better. But all three of them do work for elastic collisions. They are all laid out as such on your formula sheet. It says, where is that? Right here. Conservation of kinetic energy. Kinetic energy initial equals kinetic energy final, or describes it slightly differently, but V initial, yeah, it's got this formula here specifically for a 1D, two-object elastic collision where kinetic energy is conserved. So the formula sheet does lay out those rules as well. So I'm going to recommend we use this one, and we'll be able to figure out the final speed of both vehicles. Any questions before jumping into that? All right. So, again, it's very specifically 1 initial minus 2 initial equals 2 final minus 1 final. So we have to pick which one is which. I'm going to say that the car is 1 and the truck is 2, just because that's the order I wrote them on the other side. So that means V1 initial is the truck's positive 45, sorry, the car's positive 45. Object 2 initial is going to be the truck's negative 45, because they're moving in opposite directions. So that's going to end up being 45 minus negative 45. That adds up to 90. It does not cancel out to 0. So 45 minus negative 45 equals VF2 minus VF1. Being consistent from the other side, that would end up being VF truck minus VF car, if 1 is car and 2 is truck. So this now is our second equation with 2 unknowns. Same 2 unknowns. I'm going to recommend rearranging this for VF truck, just because then we can add positive VF car to the other side and get rid of the negative sign. So this next line down here, the 90 is 45 minus negative 45, so 45 plus 45 is 90. add VF car to the other side. So 90 plus VF car equals VF truck. And now we can use a 90 plus VF car instead of VF truck. We're going to take that, bring it over to our momentum equation, and figure out the car's final speed. Initial side's already sorted, so this is just the final side. 400 times unknown VF car plus 2,000, and now instead of VF truck, we write 90 plus VF car. Eliminating the second unknown, and now we just have to use the distributive property and a little bit of algebra and not have to deal with a squared inside a square root. We're gonna have to distribute that 2,000 into the parentheses before we can do anything else. So 400 VF car plus 2,000 times 90 is 180,000, and then 2,000 times VF car. Any questions arriving at this point? All right, I'm running out of board, so I'm going to continue vertically here for the next lines. I'm going to leave all the VF car terms on the right, and that 180,000 term that doesn't have a VF car has to be brought over to the left. I'm going to have to subtract it over, so that's going to look like negative negative 72,000 minus 180,000. And then on the right side, the two VF car terms can add together normally. So that would be 2,400 times VF car. Feel good? All right. Just a couple more lines to go. The two big negative numbers on the left can technically add together as well. That's going to look like negative 252,000. And then if we want to get VF car by itself, we have to divide both sides by 2,400. And all that said, we should land at a final answer for the car's final speed of negative 105 meters per second to the left. Any concerns, issues, or differences in answer based on math? What will you make me do? That's fine. Humans yawn. It happens. So, is that number good or bad for the sports car?
Terrible.
Terrible. Why is it terrible?
It doubled in speed in the opposite direction.
Doubled in speed in the opposite direction. So not only, it didn't even really speed up times 2. It kind of really sped up times 3. Because it was going 45 forwards. That means it had to be slowed down enough to come to a stop and then get knocked 105 meters per second backwards. So what is the delta V of the car?
45 minus, no. Yeah, 45 minus negative 105.
Almost. You got it a little bit backwards because delta is always final minus initial. So that would be negative 105 minus 45 to create a delta V of negative 150 meters per second in like a, yeah, negative 150 meters per second taking place in like a millisecond. Most car crashes tend to. That is a very big change in velocity in a very small amount of time. I made these cars driverless because it would not be pretty if a human underwent that acceleration. Let me figure out something real quick. If I assume that took place over a millisecond, that would be an acceleration of 150,000, which is 15,000 times stronger than gravity. That'd be 150,000 Gs. Pilots don't even undergo that. Pilots do like 10 Gs before they go unconscious. 150,000 Gs, no, 15,000 Gs, you're probably a puddle. And again, this is why cars do not crash elastically. It is bad for everyone. It's even bad for the truck, and we can try to prove that too, because now that we have the car's final speed, we can figure out the truck's final speed as well. So that would be 90 plus negative 105, which is negative 15. So the truck was moving at 45 to the left, now it's moving at 15 to the left. Which is actually only a change of 30, but 30 meters per second is still a lot. Like, that's like going from 60 miles per hour to 0 in a millisecond. No way. 45 miles per hour to 0. It's still not good. It's bad. Like, the truck still loses, it's just the car loses more. So elastic collisions are bad for all involved. That's why we only ever use them for, low mass, low speed sports equipment, basketballs and bouncy balls and things like that. And bumper cars, which again, low speed. So, the concept of elastic collision bad, does that feel bad for car crashes? Is that made clear at least? All right. And this is why, again, why car bumpers are not made of rubber. It is a pain to have to fix them after every fender bender, but it's better to fix your car's bumpers than to get launched into oncoming traffic and have to fix your everything. I'll also point out that both vehicles would have the same magnitude of impulse. Hold on. I like using the same color when possible. That's a good truck. That would be negative 15 minus negative 45. So the truck's change in velocity is actually positive 30, which means it slowed down from the negative's perspective. Note that the truck has 5 times the mass, and its change in speed was 5 times as small. Again, same impulse, but that same impulse affects the different masses to different levels. If you're driving and you run into a mosquito, your car and the mosquito have the same impulse, it's just the mosquito's change in velocity is enough to atomize it and the car doesn't notice. All right. Questions, concerns, vague emotions? All right. With that, that's all the information in Chapter 6. So what I'd recommend you guys do over the weekend is look over the Chapter 6 homework, because there's a lot of different types of examples in there that I want you to see and test out and experience. Even if the example doesn't look quite right, quite like something we've done, I promise we've looked at something like it before. get the homework loaded, I'll try to show you that. Whenever I don't pay attention to WebAssign for 5 minutes, it logs itself out. So, one moment. For example, the homework has an astronaut example where someone in space is going to start at rest with their tank and then throw the tank away from themselves and to now drift apart. That's technically an explosion, like the cannonball question that we did. Same is actually true for this one as well, because we've got two people standing on ice, so no friction means that as they throw the snowball, they technically explode away from it. Ballistic pendulum is well, that's a concept question. It doesn't actually have any mass involved. This one's just a normal inelastic collision. So I promise we've covered all the information that you need, even if it doesn't quite look the same. Like technically the cannonball question is the same as the throwing something away from yourself in space question. So just look over these over the weekend. Send me any questions you have, any issues you run into. We can also talk about them in class on Monday as well. Main thing that I really want to do for right now is actually begin talking about next week. Begin looking at chapter 7, because chapter 7 is about rotation. It involves kind of a change in perspective, a different way of thinking about things. So I want to lay out some new concepts, some new definitions for that, so that we can kind of hit the ground with it rolling, pun not intended, next week. Jump straight into covering on Monday what we need for lab next week. Because next 3 labs I have planned all involve rotation, actually. So again, main goal for today is we're gonna, for the rest of today, not gonna take very long, is just beginning chapter 7, getting those initial assumptions, initial definitions out of the way. Does that sound fair? All right, so. Very last thing before the weekend, won't take very long. Chapter 7 is actually the first of 2 chapters on rotational motion, because rotating takes a surprising amount of thought, has a surprising amount of variables just dedicated to rotating, as it turns out. The reason that it takes so much time to think about is rotation's kind of interesting. Everything we've talked about up until now hasn't been rotating. All the motion we've described thus far has been linear in nature. The term linear meaning of or referring to straight lines. It's literally line R. So all the work so far has been straight lines. You know, displacement, velocity, and acceleration in straight lines. Because even 2-dimensionally, it's just a straight line in 2 axes at once. Forces all point in straight lines. Momentum vectors all point in straight lines. Everything's been lines up until now. The problem with that is that it is possible for something to be moving not in a straight line. There are forms of motion that don't involve lines at all. Behold, the big dumb wheel of science, the disembodied bike tire of science. I am now going to make this wheel move. Is this wheel moving? Is this wheel actively engaged in some form of motion? You're all nodding your heads yes. Good, this isn't a trick. The question though is it moving in a straight line? No. Do the variables and measurements that we've used so far apply directly to this? Technically, no. You can't really tell me how many meters forward it's rolling because I'm technically holding it in place, but it is definitely moving. How would you describe this motion?
Rotation.
Okay, good. Sorry, let me I meant to ask a slightly different question. You are correct though, this is rotational motion. If I asked you to tell me how much this thing moves, what sort of information would you think to give me?
RPMs.
RPMs, very good. That's rotations per minute. That would tell me how many times it has spun in an amount of time. If I asked you to tell me how far it rotates, what sort of information would you think you'd give me?
Circumference, wait, no. How far it rotates?
Mm-hmm.
Well, angles are involved.
Angles are involved, yes. If I asked you how much this thing spins, you could tell me how many angles it rotates through.
360 degrees.
Yeah, one turn is 360 degrees, so 2 turns is 720 degrees, so on and so forth. Different ways of describing this thing's rotational motion, slightly different framework, but it's still connected to the framework we've been using. The number of degrees it turns through is actually synonymous with old-fashioned displacement, because it's still how much does it move, it's just moving through angles instead of meters. And RPM is a different way of saying velocity. It's amount of motion over time, amount of turns per time, instead of meters per time in a straight line. So a lot of the logic and concepts we've talked about so far do still apply to rotational motion. It just requires kind of a shift in thought. Rotational motion can still be described using all of our old terms, displacement, velocity, acceleration, and all the stuff we've been using up till now, but it involves literally just rotating instead of moving in a straight line, and it involves describing some way of describing the amount of turning, like using angles and degrees instead of using meters. And it's important to be able to describe rotation as its own entity, because rotation can exist separately from linear motion, like how linear motion can exist separately from rotation, but it's also possible to have them both take place at the same time, like if the wheel was rolling forwards, it's doing both at once. So it's important to be able to describe them separately and see how they are similar so that it makes sense when they are both taking place at the same time. So what we're going to do today is just define these beginning rotational concepts so that we can use them next week. So, first rotational concept is we need to be able to describe the magnitude of rotational motion. The magnitude of linear motion is just delta x. How far does it move in a straight line measured in meters? And the rotational counterpart to that is how many angles it rotates through. Delta theta. Same theta as in your trig questions, because that represents an angle measure. In fact, I'm actually going to tab back for a second. Note here again, length of a straight line versus degrees of an angle. That, again, affects the names linear versus angular. Everything up till now has been linear, so you can kind of note that in your brain. Everything chapter 6 and prior was linear, because it's line of lines. And your formula sheet actually mentions this technically. I haven't acknowledged it yet, but our first 4 formulas are in a box labeled linear. That is different to angular, which is a synonym for rotational. I'm going to be using them interchangeably because they are interchangeable in my brain. When I say angular, it means rotational. And the word angular means I'm referring to angles, rotation. So that is where the word comes from. It's opposed to the word linear because it's angles instead of lines. And when I say angular, it means rotational. I just want to make that clear, because which one comes out of my mouth just kind of is a coin flip. Does that sound okay for now? Okay. So, rotationally speaking, delta theta can be thought of as a direct analog to delta x. Delta x is meters in a straight line. Delta theta is how many angles has something rotated. And you can use it to describe the magnitude of the rotational motion. And it's the same as saying how many times something has spun. rotated twice, 720 degrees, 4 pi radians.
So we're not using degrees.
Yeah, unfortunately not. Now, this does not mean that you have to do trig in radians. We're actually not using any trig for right now. Basically, trig is dedicated to the first half of the semester, and then also it reappears in the final. But the second half doesn't involve that much trig. So we're using theta, we're technically talking about, rotation through angles, but we technically need to be using units of radians for these new formulas here that are labeled as angular, just because they're designed to take radians. Degrees and radians measure the same thing. You can convert between them. This is the conversion. 360 degrees equals 2 pi radians. That's literally 2 times the number pi. So 2 times 3.14, 6.28. Radians are weird, and I admit, I don't like them. I think in degrees more than I think in radians. And again, the good news is you do not have to do trig in radians. You do not have to take your calculator out of degrees mode. Any radians that we use are just going to be plugged into a normal non-trig formula. Does that sound okay? And I promise I will help with the conversions making sense. Technically, just saying number of rotations is also a unit for delta theta, because it's how much did it rotate. So that's why the RPM meter in your car is rotations per minute. It's rotations per minute and radians per second are, the same relationship as miles per hour and meters per second, basically. So there's technically 3 units for theta between rotations, radians, and degrees, but we're going to try to stick mostly to radians. And that's honestly the biggest difference between the linear stuff and the rotational stuff is linear motion. Linear motion is meters in a straight line. Angular motion is radians rotating. That's the biggest difference. Other than that key shift in perspective, all the other logic that we've already learned is technically still true for the rotational stuff. For example, you mentioned RPMs. You can tell me how fast that something is spinning, and your car does that for you. It has a meter for it. And the relationship between angular displacement and angular velocity is the same as the relationship between linear displacement and linear velocity. Linearly, if you are moving a distance over time, that tells you how fast you're moving. The same is true rotationally. If you rotate some distance over time, that tells you your rotational or angular velocity. So it's the same logic and technically the same formula. It's just using radians instead of meters and Greek instead of the Latin alphabet. Speaking of Greek, this is the symbol for rotational velocity, angular velocity. That is technically lowercase omega. Uppercase omega is the inverted horseshoe. Lowercase omega is this weird W-looking thing. I always kind of thought it looked more like a, villain mustache when I was growing up. You may call it W. You may call it mustache if you want to. I'm likely going to, if I'm reading this out loud, I'm probably going to say omega equals theta over t. So I just want to make that clear. It's technically an omega. Bless you. And all the same original logic for the first formula still works here. It's just radians per second instead of meters per second. It's still the rate at which it is currently moving. Is that logic track for right now? Okay. Now, what was the concept we covered after velocity? Going down this list. Acceleration. If velocity changes, you are accelerating, and the same is true angularly, rotationally as well, because the bike tire can start at rest and then speed up as you start pedaling. So you can have angular rotation as well. Linearly, Acceleration is the change in linear velocity over time. Angularly, angular acceleration is the change in angular velocity over time. Again, all the same logic applies. The unit for this, though, is radians per second squared instead of meters per second squared. And the variable, you might not notice a very big difference, and I wouldn't fault you for this. This is English lowercase script a. This is lowercase Greek alpha. And the only real difference is the orientation of this little upward pointing leg here. On alpha, it points more prominently outwards. On English A, it mostly points up, and it's technically smaller. It's not a big difference. It's one of the most annoying parts of the course, if I'm being honest. And for that reason, if I'm writing them on the board, I try to make them more visually distinct. A, I don't even draw the upper stem, and alpha, I just draw a fish. I think technically the Jesus fish comes from Greek alpha. I'm not 100% sure on that, but I feel they're connected. Alpha and omega and all that. And so when I'm reading this formula out loud, I'm likely to say alpha equals delta omega over t. You are allowed to call it fish though. Fish equals W over t if you want. Again, when I'm writing it, I'm going to draw the fish to make it as clear as I can. I overemphasize this leg and I kind of extend out the A itself. Literally, it's just the Jesus fish when I do it. Questions on the concepts and any issues with the way I distinguish them in my handwriting. By the way, you're also allowed to, I encourage you if you want to change all the alphas on here to make them easier to tell apart if you want. Draw fishes over them, whatever helps your brain. All right, sounding okay so far? It really is all the same concepts. I honestly tell my students to think about linear versus angular as parallel dimensions from sci-fi. It's the same basic universe, it's just spinning in radians instead of meters and straight lines. Literally, same exact parallel, just that one major difference. Things are spinning and Spock is evil. It's just a parallel world. And the parallels don't stop there, because every single linear formula we have technically has an angular universe counterpart. It's just you replace all the old-fashioned linear variables with their rotational Greek counterparts. We already looked at these two, but even formulas 3 and 4 have counterparts as well, because if you're accelerating over time, you are displacing. If you've got your bike and you start at rest and you begin pedaling, initially you're not rotating, and then as you accelerate the tire, you will be rolling forwards as that happens. And as that happens, your speed changes from final to initial. Sorry, reverse that, initial to final. Same formulas, same logic, just spinning in radians instead of straight lines and meters. So what we'll be doing next week is utilizing these angular counterparts, comparing them back to the linear ones, because it is possible to move angularly and linearly at the same time, namely if something has wheels and those wheels are spinning, because if a wheel is rolling forwards, its linear displacement forwards is tied directly to how many times it spins, right? If a wheel spins once, it moves only so far forwards for that one rotation. They're tied together. And that's furthermore why your formula sheet has had these two boxes set parallel to each other the entire class. I've just never acknowledged it until now. Your sheet is designed to show the parallels as well. There is a weird box in the middle, and these three formulas are designed to help transform linear into angular and vice versa. Again, if a wheel is rolling forwards, the distance it moves forwards depends on how many times it's spun. how fast it's moving forwards depends on how fast it is rotating, etc. And so this is one of the things we'll be working on next week, translating between the two worlds. And talking about a few other related concepts like centripetal force, which is what lab next week is about. How do you guys feel?
Are you gonna do the tire thing with the centripetal force?
Yes. Yeah, this this thing is just gonna be living in the classroom for about 2 weeks, because not only is it just something that I can use to physically show rotation, but, well, to kind of give the game away a little bit, there's a few other tricks to this. For example, while it's spinning, you can use it as a gyroscope. And a couple other related principles that we'll get to. I think you were mentioning like standing on a platform and turning it. I got one of those too.
Yeah.
So again, today's just introducing these concepts. Next week is practicing them. That sound okay for now? Any questions, objections, concerns, last things before the weekend? All right, in that case, again, please do work on chapter 6 homework, because I'd like to know what issues you possibly encounter looking at the different types of collisions. Come prepared to start talking about spinning things next week, and have a great weekend. Stay dry, assuming it's raining.